Hello to those watching online. I'm David from the Maths Learning Centre, and that'll do. The reason I'm wearing a jacket is because I can't figure out how to turn off the air conditioning, and the vent is right here behind me. So that's why I'm wearing a jacket. I wasn't in the one earlier, and it didn't turn out particularly well. So this is a Maths 1B revision seminar for those of you listening in the future, and I'm going to talk about improper integrals. Okay, so improper integrals really belong in the course wherever it is that you do limits, because improper integrals are in essence all about limits. So that's where they belong. So I will probably just put them under their own heading on the website because it's not obvious that that's where they belong, but that is where they belong. So an improper integral is an integral where one or both of the it's a definite integral where one or both of the ends, it's not possible to calculate the function value at that point. So it's a definite integral where one or both ends is undefined. I don't know if there's a proper definition in your notes. It's not really important. They won't ask you for the definition of it as far as I know. And there's different ways that it can happen. So, for example, that, for example, is an improper integral because infinity isn't a number, so it's not actually defined at that end. So it's improper at both ends, this one. It doesn't have to be infinity at both ends, so it could be something like that. It could be just infinity at one end. I don't even know if that one exists. I'm just writing down what the idea is. And there's ones that don't involve an infinity, which are also improper integrals. So something like that. The reason this one's improper is that this function isn't actually defined when x is 0. Something like that. So ones with infinity in them are obvious because infinity is not even a number. But sometimes an improper integral is one where there is a proper number there, but the function doesn't exist there. Okay, that's what improper integrals are. And the integral either exists or it doesn't. So some of them, you can write these symbols on the page, but it doesn't actually represent an actual number, and that's when the improper integral doesn't exist. Or it may be that there is a reasonable number that this could mean. Being a definite integral means it ought to be a number. So that means that the answer is a number. Or the answer could be it does not exist. They're the options that we could get. It either will come out to be a number. The number could be 0, it could be 1, it could be 462, it could be pi, or it might not exist at all. And that's what we want to know. Now, from a mathematician's point of view, You can totally write symbols like this on the page, but the question is, does that even mean anything? And so we have to define what it means to talk about a definite integral when we use numbers where the function isn't even defined at that point. And the way that we do that is we use limits to do it. So this at the moment is meaningless according to our usual definition of the integral. Our usual definition of the integral involves doing an antiderivative, and, well, actually that's not the definition. Our usual method of doing an integral involves doing an antiderivative and subbing in those points. But this function doesn't have an antiderivative at 0 because it doesn't exist there. So we can't technically do it. And even our ordinary definition of what the integral is back in Maths 1A, which is all about upper and lower sums, well, that leftmost interval of that one, the upper sum doesn't exist because it doesn't have a maximum. It goes all the way up to, but not including 1. So there's no number that you can pick that's sort of the maximum. I suppose you could pick 1, which is definitely bigger than everything. So we need to adjust our definition in some way. And so our way of dealing with that is that we say that if it's an improper integral at one end, let's suppose it's at the top, so going from a to maybe infinity, then what we'll do is we'll integrate it the way we normally would, but we'll do it up to an unknown number. And we'll just say that after we've calculated this, which will turn out to be a formula involving b, then we'll do the limit as b goes to infinity. So that's an improper at the top. Improper at the bottom is the same, including if it's got a number down there, for example. So we may have to be a bit creative. Damn it, sorry guys. This is what happens when you make these things up after having requests the day of. So let's suppose this function doesn't exist when x is a, and so what we'll do is we'll go the limit as maybe t goes to a. Actually, that sounds like a good idea, to just call it t, because then I won't get confused with a b representing an actual number. Yeah, I like that. I like that plan. It's a good plan. T is a great number to use when you don't let it to use when you've already used x. Okay, so that's the basic idea. It's a limit. So really the best way of understanding that is to do an example of it. I don't like my chances of integrating sine x over x. I'd have to do that by parts, probably. Let's see if this one works. I'll do this one in the middle. So this is the same as the limit as t goes to infinity of the integral from 1 to t, like that. So what we could do it on the page the way I'm about to do it, which is just to do equals, 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 equals. That's fine. And I might show a different method of writing it down when I do the second example. So what we need to do is we need to figure out what this is before we do anything else. So that limit is going to be dealt with last. It's the last thing to do. Now let me think. It's my list. Rewrite it. Yeah, that'll work. So we'll have power goes up by 1, divide by the new power, 1 to t. So I'm basically ignoring that limit and just copying it down every time. So this is like minus 1 over x from 1 to t. which is the limit as t goes to 0 to infinity of minus 1 over t minus 1 over 1. Yep, the top is t. So the limit as t goes to infinity of 1 minus 1 over t. If I'm just creative, that will become a plus 1, and the minus 1 over t is there. So now that I've done the whole integral, the whole definite integral, and subbing in the top and the bottom, might put some brackets around that so it's a little easier to see what just happened. Okay, now that I've done all of that, I can now do the limit. So the limit of 1 is 1. And the limit of 1 over infinity, not that 1 over infinity is a thing, but the limit of 1 over t as t goes to infinity is 0. And so the answer is 1. Yay! So let's see if we can fit that all on the screen at the same time. Not quite, but most of it. So that is the idea. That's pretty much all there is to it. Except there's a few other little quirks that might happen. There was a famously difficult past exam where they had one that was improper at both ends. So I might see if I can find that one in just a minute. Just let me fiddle with something over here on my piece of paper so that I can be confident that I'm going to figure this out. No. Okay. So, has anyone seen any of the past exam questions that's got improper integrals in them at all? Off the top of their head? That's all right. It's just going to be easier for me to get a pre-existing question than to pull one out of my head. I may also just... Okay, here's one. So let's check out this function. So at the moment it doesn't look like an improper integral just from the fact that it's got numbers in it, there's no infinity. But if I look very closely, my function isn't defined when x is 3. So this is an improper integral. If you ever see one in a context where someone's asking you to prove that you know how to do improper integrals, you know, either you're mugged in the street or you'd have an exam, then that's what you'd need to write down. You need to give a reason why it's improper. If it's got an infinity, then that's sort of, well, duh, but with a number in it, you need to give a reason why. So being improper at the top, it's not improper at the bottom. This function totally exists when x is 0 because it's 1 on root 3. So that's okay. That means that we now define it as a limit. So what I'm going to do is to prevent myself having to write lim over and over and over, I'm just going to separate this into pieces. So I'm just going to figure what this is out straight. Now let's see. Okay, so 1 on root would be something to the half, which is a power, and I can deal with that. Like that.
Wouldn't it be negative a half?
It would totally be negative a half. Well done. Guy did a really bad one yesterday. Was doing polynomial division and totally got everything completely backwards and had -1 minus -1 being -1 plus 1. No. It was 1 plus 1 equals 0. That's what I did yesterday. Oh, man, it was awful. So, because it was 1 minus -1, and then I just said it was 0. Anyway. Okay, so there we are. That's why when I do exams, I always check every time I get to the end of a question and go back and check all my minuses, because I know that that's something that I'm likely to do. I can't stop myself doing it, but I can at least know that I need to check. So there we are, 3 minus x to the minus a half. So I can integrate that, because if that was just at x, I'd know what to do. And since the thing inside there, the derivative, is a constant, I can just pretend it is an x and divide by that constant as I go along. So the power will go up by 1, which will go up to a half. I'll divide by the new power, which will put a 2 there. But then I'll have to also divide by that minus 1. If it was 3 minus 4x, I'd have to divide by minus 4. And so I get minus 2 root 3 minus x, 0 to t. So let's see what we get. When we put t in, we get 3 minus t. And 0. So that's what we've got now. When we sub in the t, we get this. When we sub in the 0, we get this. And so we've got minus 2 root 3 minus t plus 2 root 3. That's a classic mistake that lots of people make as well, is to just assume that because this is a 0, the answer is 0. People do it over in dynamics all the time. So just keep an eye on that. Explicitly sub it in, because it might not come out to an answer of 0. Okay, and so now what we're saying is that the integral from 0 to 3 of 1 over root 3 minus x dx is going to be the limit of this. Oops, sorry. It's going to be the limit of that. You see, I only had to write lim once. Sweet. Shaves vital milliseconds off. And so now I can just, well, root 3 minus t is totally defined when t is 3. I can just sub it in. And that's what it's come out to. Because 3 minus 3 is 0 and root 0 is 0. I'm just checking something. No. Okay. Now I should say that the way that people design exams is that they try and do more than one thing at once. And so it's likely that you'll get an exam question that will involve an improper integral that will turn out to be some limit that will require a specialist technique to solve. I can't think of one of these off the top of my head. If you give me a minute or two, I might be able to think of one. Give me a second. No, it's just not going to happen. No, I'm sorry, I can't do it off the top of my head. But all I'm saying is that these limits that I've done here today have been nothing more than just subbing stuff in. Okay? But it may be that the limit you end up with at the end will be like sine x over x when x goes to 0, which you know is 1. Or it will be something that's like x over x, x plus 1 over x cubed, and what you need to do is L'Hopital's rule. And so don't forget that you are allowed to and expected to apply the other things you know about limits to these limits that appear when you do the integral. But I can't think of any off the top of my head that when I do the integral will turn into something that you need to do that for right now. But just I might write that warning down. To do, e.g. L'Hopital's rule, just as a warning. I guess the only other thing to do would be an example where it's improper at both ends. And let's see if I can find that. That one, for example. That's improper at both ends. Be very careful because some of them are improper at both ends even though only one of them's an infinity. So there are some of them where it doesn't exist when, maybe it goes from 0 to infinity and it doesn't exist when x is 0 either, and so it's still improper at both ends. But this one's improper at both ends. It is subtly different from this one. And the reason I've chosen this new one is because this one, I can't do that integral. Like, no one can do that integral. There is no formula for this integral. This one I can do, though. So this one's improper at both ends. And so the only way for me to deal with this is to split it into pieces so that it's only... So I've got two pieces and each of them's only improper at one end. Because currently my definition of an improper integral only works at one end. So what I'm going to do is I'm going to split this into the bit from minus infinity to 0 and the bit from 0 to infinity. Like that. That's the way of dealing with it. Turn it into something that involves a number. Like stick a number in the middle and do the integral for up to that number and then from that number. And then each of those can be calculated separately using a limit. So that's what we're going to do. Now, since I'm going to have to do this integral twice, the quickest thing is probably to do an indefinite integral first. Since I have to do it twice, I might as well just do it once. Oh, what's on my list? So can I just do it? If it was just e to the x, I could, but it's not. What's next on the list? Rewrite it. Not likely. Substitution. Oh yeah, if I did u equals minus x squared, x is nearly the derivative of minus x squared. It's just out by a constant, so I reckon we'll be good. And so, minus 2x dx. If I divide by the minus 2, I'll be good. Beautiful. And so the x dx is du, and that is minus a half of du, and which means I can do it. Next page, I reckon. So the integral of x e to the minus x squared dx is in fact that, because the x dx becomes a minus a half du. And so the minus a half is multiplied on, so it will still be there afterwards. The integral of e to the u is e to the u. Beautiful. Sorry about that. Excellent. So let's see. The integral from t to 0 of x e to the minus x squared dx is minus a half e to the minus x squared from t to 0, which is minus a half e to the minus 0 squared minus a half e to the minus t squared. Okay. E to the 0 is 1. All right. What's the limit of that? Okay, so the limit of minus a half is still minus a half. E to the t squared, if t is going to minus infinity, then t squared is going to plus infinity. And e to the infinity is going to infinity, and 1 over infinity is 0. So I'm just going to write that reasoning down. T goes to minus infinity, means that t squared goes to plus infinity, which means that e to the t squared goes to infinity, which means that 1 over 2 e to the t squared goes to 0, because it's 1 over infinity. All right. I think I'm just going to write equals minus a half since, and now the working looks like real working. Okay. So what about the other end? The limit as t goes to plus infinity of 0 t x e to the minus x squared dx. Oh crap, sorry. Not up to that yet. Let's just go back to where was I? I've done this bit, haven't I? That's the bit that I just did. Yep, so now I need to do this bit. Okay, so I need to do, so the integral from 0 to t of x e to the minus x squared dx is minus a half e to the minus x squared from 0 to t, which is minus a half e to the minus t squared minus a half of e to the minus 0 squared, which is now e to the 0 is, so that's plus a half. I think that's right. Seems reasonable. Okay. Nice. Now that makes sense. Like that half is what I get when I sub it into one end, and the other one I've minused it. So they should come out, you should, when I do it on two sides, you should sort of get a number in the middle that's minus on one of them and plus on the other. So that makes sense, I think. So the limit as t goes to plus infinity of 0 to the tx e to the minus x squared dx is, as t goes to infinity of minus a half e to the minus t squared plus a half. Maybe I should have done some simplifying earlier. Oh well. Okay, the same argument's going to make that come out to 0. T goes to infinity, makes t squared go to infinity, which makes e to the t squared go to infinity, which makes the whole thing on the bottom go to infinity, and 1 on infinity is 0. It distresses me that this answer is going to be 0 because the integral of this should not be 0. Oh, it totally should be. It's a bloody odd function. Anyway, sorry about that. So this is going to come out to the answer we got for this, which came out to minus a half, and the answer we got for this, which came out to a half, which comes out to 0. How unsatisfying. As I said, it's an odd function. The integral of odd functions from one side to the other is always 0. Anyway. Unfortunately, though, you can never be completely sure of that when there's infinity involved. Weird stuff happens. Actually, you probably can, as long as the limit exists at all. All right, well, there you go. That's improper integrals. Does anyone have any thoughts or questions they want to add to that? Yes?
Can you use symmetry?
Sorry?
Can you use symmetry?
Can I use symmetry? Probably. So you're saying since it's an odd function, just say it's 0? I have a feeling I could have done it that way, but I would still need to use the limits. So I could have done it this way. And done it as the limit as t goes to infinity from minus t to t. Like that. So make it slowly wider and wider. And then say that this is 0 since it's an odd function. Because the function's symmetric. Which is 0. I could have done that. But I have a feeling that my judgment of whether that was okay would be based on trying to figure out what was in the lecturer's head when they wrote the exam question, which would usually be based on how many marks it's worth. So if it was only worth 2 marks, this is what I would do. Whereas if it was worth 5 marks, I'd probably do the other one. Just to prove that I knew how improper integrals worked. Or you could say, like with a 2, it's 2 times this one, but it won't be 2 times this one because it's an odd function. If it was an even function, then you could do it that way. Anything else before I move on from that? Sweet. So my instinct is that this is less hard than it looks to begin with. I mean, mod having to know how to do limits generally. It's just sort of one step away from the limits. Got to do something first, which is an integral. Cool.